Hello, everybody, and welcome to another edition of Canadian Genius. Today, I thought I'd get off of human a little bit and go towards the realm of science. Because, as I said before, there's many things I want to talk about, like temporal mechanics and all this other stuff. Now, I'm not sure we'll get to temporal mechanics specifically, because that's a bit of a bigger topic, but I did want to tackle physics itself, because there's a lot of things that I've noticed watching science shows and reading books and whatnot, and there's a few concepts that are very commonly held that, based on my understanding, are flawed. Because, as I said before, the way my brain works is I need to kind of be able to look at something 87 different angles and analyze it and figure it out and understand it before I can keep it and understand it fully. And as I've looked at some of these topics, there's things that to me seem blatantly obvious that there's something missing, but that other people just don't seem to notice. So I don't know if it's that, they've covered that and it's just not talked about because it was dismissed, or if it's because they just hadn't thought about it yet. But with a lot of things and a lot of the history of humanity, we often overlook very simple things because we're kind of caught up in the bigger thing. And with science especially, it's not uncommon to kind of develop a bit of groupthink, which just means that everybody kind of thinks the same things, right? You're indoctrinated into this methodology, right? You're taught the same textbooks, you're taught the same equations, you're taught the same way of thinking. So then most people end up with a similar way of thinking, right? It's not a bad thing. It's just kind of the natural outcome of the way we disseminate information. But at the same time, because we do that, it makes it so that we often miss the blatantly obvious because we're just not thinking that way. And that's why I want to share what I know, because I don't know if it's been accounted for and discounted or if it's never been seen. And I won't know until I account for it and somebody comments on it. So to start, I wanted to talk about things like just physics itself and maths and the equations that are used. Now, as I said before, I didn't do good in math and stuff because the equations were subjective. And I think some people that might be a little misunderstood because when you understand it in more detail, they are more definitive. But the truth is, I'm not talking that they work because everything is based on everything else and together they work, which is what physics essentially is, but the equations themselves and where they come from. And to tackle the first one, I'm going to go for the one everybody knows, E equals mc squared, Einstein's great mathematical equation. But what does it really mean? And that's kind of the one of the keys that I think people miss, is that it doesn't actually mean anything. Einstein just created a standard. It could have been anything. It could have been E equals mc cubed. It could have been a whole bunch of different things. But everything else is based off of that. So it's an anchor point, but it's not in and of itself meaningful, right? If Einstein could have easily come up with six other equations that could have done the same thing. But that's the one he came up with because that was the one that fit, right? That was the one that worked best. That was the one that made the most sense. But because it's an anchor point, it kind of becomes justifiable because everything else works because it works. But that doesn't mean it's less subjective. And I think we need to remember that. Because if we never challenge this idea that E equals mc squared, we can never find an alternative variant. And unfortunately, with complex math, a teeny tiny microscopic variation can mean billions of things are wrong in the end result because of how massive they become, right? It's all compounded issue. And so that's why I wanted to look at that one first, because if we don't understand that it was essentially subjective when it was first created and is, even though it's a linchpin, could easily have been something else, then we can accept that the future, it may change. And we've seen that with a lot of things in the past, that we say that this is factual, this is off, like it's non-negotiable. And then we understand more and realize, oops, it wasn't. And a part of that is our arrogance, that we think that we're superior, that we're better, that we're more right than everybody else. And a lot of times with science, it's about popularity. that determines who's correct, not evidence. And for that reason, that's why I wanted to tackle some of this stuff. I mean, it all relates to humanity in a sense, but if we ever look at something as non-negotiable, that doesn't work. I mean, every scientist on the planet will tell you that that is the fundamental precept of science, that everything is negotiable, that it's not proven until it's disproved, right? There's always that potential. But we get into this arrogant methodology that it's no longer allowed to be disproved. And that's not helpful because it puts us in a state of atrophy, right? If there's no new blood coming into that idea, there's no possibility of discovering new things. And because that's an essential component of physics, if we don't ever look at the fact that it could change, then we'll never accept it. But along with that comes the theories in physics. And a good one that I want to talk about is light speed, which in E equals mc squared is the c. That's the speed of light. So if we look at light, one of the things that we theorize, or Einstein theorized and is very held belief, is that as soon as we get to the speed of light, our perception of time would stop. But if we look at reality, that doesn't make sense because we do things near the speed of light and they don't stop. So what we're talking about is a misunderstood perception because we have things like the Large Hadron Collider that take particles and spin them at almost the speed of light and smash them together. Well, if at the speed of light, the perception is that time stops, how is it that these particles could connect, right? Because it should be that they go to a certain speed and then elongate and elongate and elongate and elongate and stop. But they don't. Now, if it doesn't work for a particle, how can it work for something more? And one of the things I've discovered as I'm looking at this stuff is that it's always talking about perception, about if the person on Earth was seeing it from a distance. And we forget that that is a perception, that's not a reality. So if by the speed of light, if my perception on Earth is that it should have stopped in time, that doesn't mean it stopped in time. It just means I only can see that. But what happens after that, we don't really understand because we stop at that perception and call it good enough. Which relates to the other one I want to talk about, and I'll come back to that, which is the Big Bang Theory. Because it all kind of connects, right? Our speed of light is sort of this maximum speed that everything can travel and is all connected to the Big Bang and forward momentum and all this stuff. But one of the things that we forget is that the Big Bang didn't create everything. We like to think that, but we know through scientific investigation and endeavor that there are alternative universes beyond our own. And we're not talking alternate dimensions. We're talking just other places that are so far away that they literally are their own entities in a different place. But they're massive and distant, and we will probably never ever get to see them because they're so big and far away. But the universe itself, even though it's expanding, is finite. It has an edge, right? So when we talk about the Big Bang, we're not talking about the creation of everything. We're talking about the creation of just our universe. And that, I think, causes a lot of disproportionate amount of understanding with certain elements. One of the big ones is time. Because time didn't start with the Big Bang. Time existed long before the Big Bang and will exist long after our universe is destroyed. But it's also a subjective thing, because time is really just the measure of forward momentum. We've quantified it into a measure of minutes and seconds and hours and months and weeks and days to fit. But at the end of the day, it is more of a subjective perception, which is why time always sort of seems to fluctuate, right? You lose time, you lose track of time. But time itself is solid, or so we perceive. But one of the things we do know is with speed of light is that if we have these wonderful devices that are called atomic clocks, and they work on the decay rate of atoms to set a very specific amount of time. The atom oscillates like billions of times a second to create 1 second on this atomic clock. And it is so precise that you can calculate like just this insignificant, minuscule amount of time precisely and do it across the board with all the other atomic clocks. And when we sent atomic clocks out into space, we discovered that there was this difference in time. But one of the problems with that is that we don't yet understand all the variables about energy itself, about mass even. We know that the universe has got most of it is this empty stuff that we don't know what to call. We don't know what to label. We don't know what to define. And we usually call it things like dark matter and dark energy because there's just no other explanation. Whether it even exists is still itself a theoretical unknown right now. But the things that we do know, we still don't know how they work, such as gravity. And I think that's one of the big issues we have with some of this stuff is that, like our ancestors, we're basing our observations on what we see and limiting it only to what we see. And because we don't have the technology to go beyond that, we get into that arrogant methodology that this is now, right? The sky is blue because I see it as blue. Well, we know it's not blue. We have the understanding now to realize why it looks blue, and our ancestors didn't. But we still perceive it that way because that's what we see. And it's an important fact because we don't know what impact gravity has, right? We don't know how gravity works. We don't know if there's gravitons. We don't know if there's some other thing. The one experiment that we have to kind of define how gravity works has nothing to do with gravity, which is to grab a bucket full of water and spin it around. That's centrifugal force, which pushes the water to the bottom of the bucket and keeps it there. That's not gravity, because if it was, the water would be on the outside of the bucket, because that's where we are on Earth. We're on the outside of this big spinning ball and aren't flying off. Why? The answer, of course, is gravity, but why? We don't yet know, right? We don't know if gravity works like magnetism and sucks us down. We don't know if it pushes us down, if it's like Velcro, and we don't know because we don't have any technology to understand it or explain it. But that's important because while we're looking at time and the speed of light, we're not able to factor in those other elements. So we can build an atomic clock, and on Earth it sets this perfect exact time because everywhere on Earth is essentially the same gravimetric pressures, the same atmospheric pressure, the same gravimetric density of the universe, the same basic matter of dark energy and dark matter and all these unknown things, right? That keeps it kind of, because our Earth is essentially just this teeny tiny pinpoint in the universe. As soon as we go outside of those things, we don't have a way of understanding whether they're having an impact, right? We know that, the astronauts have gone out and their watches come back at different time than when they left, and we try and look back to Einstein and all his theories to understand that. But we miss some basic things. And I think, like I said, because of the groupthink, right? Because we're trying to match the evidence with the science instead of trying to find a new way to explain it. And that's what I wanted to start the dialogue on, right? Because if gravity has an impact on our perception and measurement of time, it has no actual bearing on time itself. It's only on our measuring tool, right? And that's an important distinction because if we look at time as this separate thing, and like I said, I wanted to get into temporal mechanics at another point, there are so many pieces to it, and separating our ability to measure time from time is, I think, an important step to understanding time better, because we don't know what effect dark energy has on time. We don't know what effect the gravity has on time, right? We don't even know how to define that because it's just too much for us, because we just don't have a technology that can do that. Now, we have other technologies that are in development, like quantum computing, which we hope will give us a better understanding. We also have new ways of thinking, such as the unified string theory. I don't want to get into details on those. They're absolutely fascinating, but that's not the point I want to make. But as we gain more understanding, we need to always remember to look back at what was there before and realize that all of the stuff that we say is solid always, under every single circumstance, eventually is proven not to be solved. Because there's something that we didn't have before. There's some knowledge we didn't have. There was some test we didn't have. There was a technology we didn't have. And until we have those things, we have to remember that it's not necessarily real, right? Because if my measurement of time is based on something like dark energy and gravity and all this stuff, then the further away I get from Earth, it's going to change, right? Because now everything is slightly different, right? If the dark energy density at this place is different than the dark energy density at this place, time may be perceived as different. And one of the things that you hear in physics is how the laws of physics may not apply somewhere else. Well, they're not laws. That's one of the big misinterpretations people have, that a physical law isn't in stone, it isn't set, it isn't non-negotiable. We do present that way, though, and that's the problem. But a scientific law says, based on all the evidence and all the technology and all the theory we have, this is the most stable thing we understand. And everything else is based on it, right? So everything is based on E equals mc squared. E equals mc squared is the law of energy. It doesn't mean that it's right. It just means that it's correct based on what we know. And that's a very, very, very critical thing to always remember. And all of humanity, right? We do it every day. We do it at work. We do it at play. We do it on TV shows and books and everything. We assume the world is this way because to our observation, it is that way. Doesn't mean it's true, right? And we have this idea that I'll believe it when I see it. Well, if we stop and look at all of our technology, you can't see any of it working, right? My tablet has no moving parts, right? It has nothing that actually goes except the buttons. And those are only there for me. They're not there for it, right? They're user interface elements. And the same thing, right? Like we can build things like smart TVs that are that thick, that are like less than a centimeter in width. But why don't we? Well, when we did studies, we found that made people very, very uncomfortable because it felt too fragile. It felt like it was just going to break too easily. So that's why we didn't do it. But that's why our technology also allows us to do things like these ultra-thin laptops and these ultra-thin tablets. We could make them even thinner. We could make them even lighter. The two problems we have are batteries and personal opinion, right, of how it feels. And fragile is not something we want technology to feel like. But we have to remember that because our perceptions are always going to be an element, right? Our perception of E equals mc squared as solid is going to have an impact on how we view temporal mechanics, how we view space travel, how we view time, because they're connected, right? If we look at it as a transitional placeholder until we have more technology, we're not going to limit ourselves to using that as the cornerstone of our technology. And one of the things I find fascinating about physics is everything we have in technology, our computing technology, our cell phone technology, our data processing technology, is all built on one technology. It's all the same technology. It's all radio waves, right? Our whole entire infrastructure is built on radio waves. We use them in different ways, but that's all of it, right? So it works because it works, not because it's necessarily the best option, right? Most of what we do is the same that technology has evolved. It's just this led to that, and it works, right? It's not because it's the best option. It's not because it's the only option, which is why with things like quantum computing, it's such a massive discussion because it goes into things that are no longer necessarily working on radio waves. And that's also why things like EM pulses, electromagnetic pulses, can destroy a lot of things because it's all on that same basic technology. Now, could we develop things in other technology? I think absolutely. One of the things that I've always been kind of contemplating that I have no way to even think about really more than in an abstract way is magnetism. Because I kind of wonder if there isn't such a thing as specific magnetism, that I couldn't find a way to tweak magnets to be able to attract other than ferrous metals, right? Like, why can't I make a magnet that can attract a type of plastic? Why can't I make a magnet that attracts glass? Because if you stop to look at it, static electricity provides elements like that. It's not magnetism, but it provides similar elements, right? Things stick together, which is what magnetism essentially is, it's just items sticking together. But if we never stop and think that there's another way of doing things, another way of looking at things, then we're always going to be limited. And that's why the speed of light is so fascinating to me, because like I said, our perception is that if it reaches the speed of light, it will stop. But that doesn't change that it itself could do 100 other things that we just can't explain because we can't observe it. And just because we can't observe it doesn't mean it's doing something. And it's really, when you stop to think about it, it makes a lot of sense, but it's so abstract and so huge that it doesn't make any sense at all. Which is why I love humanity, right? That we have these complex minds that can think these complex thoughts that are just immense and yet so simple. So my whole point is that we get into these ruts and think that these are the way things are. But we have to look at the evidence as a whole, right? So like I said before, with the speed of light, if I can send particles down the Hadron Collider and get them to go near the speed of light, and I'm not observing them stop, like, because that's what theory says is supposed to happen when you get near the speed of light. Here's something that's actually doing it. How come it's not following that pattern? Right? And if you're saying, well, it's because you're continually putting energy in, but it's not about that, right? Because energy is defined, right? That's E equals mc squared. Once you have a mass and you have the speed of light and stuff, the energy is consistent. So adding more energy means something should change, right? Because that's E equals mc squared. That's why, again, it's somewhat subjective, but yet it's stable enough to work with our technology. Because if I take something and I keep adding energy in, the mass isn't going to change, not necessarily. I mean, it might. Well, what's left? If I add energy and I've got mass, the only thing left, E equals mc squared, which is the speed of light squared. So does that not mean that then it could go faster if I could add enough energy into it, right? And I remember years and years ago, I was reading a book. I don't remember what it was called. It wasn't a huge book, but it was really fascinating. And one of the elements that stuck in my mind was that they had technology that could rearrange atoms and use it to both generate energy as well as create different elements, right? So, for example, you could literally take lead and turn it into gold by rearranging the atoms. And so something that went from a higher element to a lower element would give you just this massive amount of energy that you could use to power things. Or you could turn it around and take that energy and stick it back into a lower element to make a higher element. And looking at science and reality and all these things, I kind of do wonder, like, why can't we do that? Now, some of it is because, unfortunately, because we get stuck in this idea of I can't see it, so it's not real, we miss a lot. Which is one of the reasons I wanted to have this discussion before I go into some of the others, because they do connect, right? There's a lot of humanity in this stuff. And we need to understand what our limits are on it before I can kind of go further. And there's a lot of arrogance in science. There's arrogance in people, right? We're people. We can't get rid of ourselves. And so it perpetuates. And like I said, a lot of it is that hierarchical popularity contest methodology, right? Einstein's the master. He's the best. So his stuff is right. Even though we found all sorts of flaws and have rectified them, but he was still right, right? And then we have all these other theories that we look at and go, well, they're right, even though they contradict this, but they're both right, even though they contradict each other, because we're not understanding how they're wrong, how they conflict. And it's because we don't understand it. Doesn't mean it's wrong. It doesn't mean it's supposed to connect. It doesn't mean it's supposed to conflict. It just means we don't know. And we're so afraid of that answer, I don't know, that we sacrifice a lot for it. I was watching a documentary on the Sphinx, and one of the big theories that everybody discounts is that a lot of the erosion that happened around the base of the Sphinx was due to water. All the evidence supports that theory, right? It's the most accurately evidenced element of why that could be, and yet it's the one thing that's neglected. Not because the evidence doesn't support it, the evidence completely supports it, but because it's not popular, right? Because it wasn't the theory of the giants of the industry. It wasn't the theory that is most supported. And one of the reasons for that is because we get into that methodology, but also because of the cost of changing it, right? If I tell you that E equals mc squared, every textbook on the planet is based on E equals mc squared, right? All the physics is based on it. If now I come up that that's not correct anymore, I now have to change the entire planet to justify for this new addition. And we don't want to do that because we're afraid of making that kind of change. We're afraid of being that person. And like I said with celebrity in the beginning, that's one of the things I'm afraid of and still am. And I think they are too. Because there's a difference between famous and being infamous, right? Hitler is infamous. Jesus is famous. Gandhi is famous, right? It's okay to be famous. It's really not okay to be infamous. And if you're the guy that changed technology, you're the one that has to deal with the repercussions. You're the one that has to deal with the consequences. And some people just don't want to go there. Which, when you look at law, a lot of times we deal with things like setting new precedents. It takes a lot of courage for somebody to stand up and set a brand new precedent, which is why laws often take so long to change, because the people are afraid to set them, because we don't know the consequence. We don't know what the aftermath is going to be. But we have to get to the point of realizing that all of this stuff developed because of our limited understanding. And it's all based on what we know. And history has shown us time and time and time and time and time and time again, and will continue to show us time and time and time and time and time again, that it always changes. That there is nothing that is set in stone. Everything is negotiable. Even stuff set in stone, theory tells us, is 99% empty space. Right? It's not really set in stone, it's set in empty space that's solid. So I just wanted to kind of open that door and get people thinking partly in that abstract way, because some of the topics I want to talk about are even more abstract than that, and are stuff that no one's really looked at yet for a whole bunch of reasons, and I'll get into that too. I just want people to realize that just because we believe something doesn't make it real. And even people like Plato had said things like, the unexamined life is not worth living. And that's what they're talking about. That critical thinking, which is what scientists are supposed to be expert at, says that you adopt this belief until new evidence comes to challenge it. And then you evaluate and take the better belief. We don't ever do that typically, because our beliefs are too important to us. Right? Our cornerstone beliefs are just, they're not negotiable. And it doesn't matter if it's science or religion or something in between. We set those. But if we want to grow beyond and develop new ways of thinking and new technology and new ways of doing things, we can't look at those cornerstones as cornerstones. They now just to be kind of evolved into placeholders. So that that is what it is until we find the better option. And that's a much better way to think of everything, right? Because when we get a better option, it all makes more sense. But part of this is because we don't educate people to think for themselves, which is another big issue, right? And like I was talking about with the girls' self-worth and stuff, about how we have all of these products just trying to crush girls to make them buy all these products. It's the same thing. They're counting on us being too stupid to know better. Or they're counting on us not thinking outside of that box to know better. And it's harmful. And it's harmful in other ways too, because we're limiting ourselves. As I said, if all of our technology is based on radio waves, how many other opportunities are we losing? Could we have specific magnetism? Could we make sorting our garbage really easy by having a row of different specificity defined magnets, that this one pulls up plastic, this one pulls up glass, this one pulls up biomatter? You know, why can't we do that? Right? Why can't we have a technology that's based on something completely different, not just perpetuation of the same idea? And I'm going to talk about technology itself as another topic, and I'll actually show you how technology evolves and why it's become as rigid as it is because of how it evolves. So I could go on a lot. I didn't get a chance to do temporal mechanics and stuff, which is good because, like I said, that's a big topic. That's a bending topic because it's really quite abstract. So I'm going to leave it at that. I'm going to come right back and do another one right away, and I'll see you in a minute if you stick by and watch. Thank you for listening. I'll see you next time.